This is the least square problem for box constraint image deblurring. Okay, this is work with my student, the Hong Changock. Okay, so let me give you my outline. The first introductions, and the second iterative least square algorithms, and the third I will give some numerical experiments, and lastly I give conclusions. Okay, this is the problems. Okay, look at the televisions. Okay, if you look at the televisions, then suppose this is the UVC image. So actually this television consists of the panel and the backlight. Okay, so if you want to have the 1 point turning on of the backlight, then there is blurred images. Okay, so the problem always happens from this. So if you know the blurring operator, okay, then you may think, okay, so we have here the blurring. Okay, so you have this AX equal to B. Okay, so this is the Vichy image, and this is the blurring operator. Then you may find X. Okay, so actually X is the actual intensity of the backlight. So you will find, okay, X equal to A inverse B, then we have done. Okay, so that's a very simple problem, but in reality, that's not simple at all. Okay, because we have the constraint like that. Okay, so we have the limit of the intensity of backlight. So X should be larger than 0 and less than 255, and you may constrain it, okay, like the X 100 or something. Okay, so you may change. Okay, so but the problem is this. So we consider this problem, AX equal to B, okay, in least square sense with this constraint. Or you may ask this: why do we use the least square problems? Actually, in order to get the more sharp image, you may use 1 norm. Okay, you may use 1 norm instead of the L2 norms. Okay, then in this case, the problems become more complicated. It's a kind of the compressed sensing problem now, right? So it's really hard problem. So actually, if you solve this problem, this gives them sharp images. But this is a preliminary study, so we just use this square problem. Okay, and then you may think, okay, so this square problem as a constraint is so simple. So okay, this is so very important problem. So you may think this kind of the functional, right? So we have these least square problems, and we have that box constraint. So you just find the minimum of that functional on that reason. So that's a very natural problem, and it's a really easy problem in the optimization world. It's already solved. Okay, but the reality is not. Okay, because in digital TV, in 1 second they they turn on and off 120 times in 1 second. Okay, and also if you consider the size of the images, okay, nowadays you have the wide screen. Okay, then the image becomes 120 times, okay, 1080. Okay, so that's about the number of pixels is about 200 million. So if you consider that problems, okay, the matrix A is 200 million by 200 million. That's amazing. Okay, so if you solve that problems, okay, more than 120 times in a second, that's ridiculous. Okay, so that's a real trouble. Okay, so our goal is here. Okay, we find fast method. Okay, so that means we want to look at some algorithm developed in the optimization world. But for me, okay, we tested a lot, but I will look at that, but that does not give us satisfactory results. Okay, instead of that, we look at some kind of image processing world. And in the image processing world, they provide a very simple and fast algorithm for this kind of the box constraint problem. Actually, that does not give the box constraint problem, but I changed. Okay, I look at the problems and I modify that into our problems. Okay, so this is the general form of convex minimization problems. Okay, so we want to minimize these functions, and we have this kind of general constraint, inequality constraint. The problem is inequality constraint. Okay, so we have this, and we have this inequality constraint. Then we have very famous KKT conditions for. Okay, here. So this is the Kawashiki contact condition. So the x star is a relative minimum on that region, and the x star is the regular point for the constraint. Okay, regular point means the that in some cases this constraint becomes inequality constraints. Okay, for that minimum. Okay, so when that constraint becomes inequality constraints, if you take a gradient for that constraint, if that are linearly independent, then we call that x star is regular. X star is regular point for the constraint. So the KKT condition says this. Okay, if x star is the relative minimum and the regular point, then there is a random multiplier lambda to satisfy this condition. This lambda is always positive or equal to 0. Okay, so this means, okay, so here, okay, suppose, okay, this is just a very simple two-dimensional case. So this is the least square functionals, okay, and here we have a minimum, and this is our reasons to find the minimum. Then, okay, yeah, if you look at that, this x star is the relative minimum, and if you check that KKT condition, the random multiplier becomes positive here. Okay, and if you take this as 0, then, and if you take the random multiplier here, then the random multiplier becomes negative. So this subspace, okay, the solution cannot have that subspace. That's what the KKT condition tells us. Okay, so the problem, actually the most popular problem, popular algorithms for this constraint problem, inequality constraint problem is active set method. So active set is actually this kind of combinatorial problem, combinatorial algorithm. It separates the constraint into two categories. One is equality constraint, and another is inequality constraint. Okay, so the problem is actually given as the inequality constraint, but if you look at the this minimum point, then some constraints become inequality constraint, and some constraints become equality constraint. Okay, so this active set method finds the equality constraint from that inequality constraint. Then, after finding equality constraint, you reduce the problems. Okay? You reduce the problems by plugging the equality constraint. Then it becomes now inequality constraint problems. Okay, but that means, okay, so the inequality constraint problem means actually the problem, now you can solve the problems inside the domain. The solution minimum happens at inside the domain, right? So that becomes now unconstrained problem actually. So you can solve the problem. So the key idea is find inequality constraint. So that is called active set. Okay. So the idea is, okay, so first guess some teachable initial point x0, for example, here, and we find the corresponding working set. Okay, so if you take x0 here, okay, then this x-axis works as the active set. We call working set. Okay, and you try to minimize the problems inside this subspace. Then, if you look at these problems, okay, then minimum happens here, right? And here, then this point belongs to two subspace. And if you look at the KKT conditions, then this space is not working. This subspace is not active set, so we drop. And this becomes now active set. So take this as the equality constraint and solve the problem. So minimize the problem. Then minimum happens here. Okay, this is the very simple idea. But if you have the very large dimensions, then it's harder to find which one is active set, which one is not active set. So okay, so anyway, so first we take x0 and we find some corresponding working set, and we find such directions. And if such direction becomes 0, then we stop. Okay, and if this is not 0, okay, we update this along that such directions. Okay, and after arriving the minimum along that direction, we check the KKT conditions. If it satisfies, that's right. But if otherwise, okay, we update. Okay, we update the active set. That is the active set method. And depending on how we choose this such directions, okay, we have several layers. So the simplest one is gradient projection method. On this subspace, we take gradient. Okay, so first we just take gradient vectors. Then gradient vector looks like that, right? Like that. So we take gradient vector and we project the gradient vector into this subspace. Okay, so that's called the gradient projection method. So this gradient projection method is this projection of the minus gradient. Okay. Okay. So another is the projected CZNR method. Okay. So in working set, the working set means xi is equal to 0 or 255. So put that into the equations. Then we have reduced systems. And in that reduced systems, we find this. We minimize these equations using this relation. So we use just the here, okay. So actually this becomes Actually, this becomes an unconstrained problem because, okay, this we already plug in this x of 0 and 255. Okay, so this becomes an unconstrained problem. So we have the conjugate gradient method for normal equations. So we find the conjugate directions. We find the conjugate directions as such directions in that subspace. That's called CZNR method. Okay, that's called the projected CZNR method. Okay, so this is a little bit better than the projected gradient method.
What's the A tilde? The A tilde?
A tilde is the reduced problems. Actually, we plug in x equals 0 or 205 because we already assume that the solution happens for some index xi equal to 0 or 255. So we have the reduced systems.
So it's just the A reduced.
Yeah.
You're taking out the inequality then as well, right?
Yeah. So we just think the only inequality constant actually, but that is not constrained at all. Right? It's an unconstrained minimization. Right? Okay. So that's method. And the other popular method is dual primary interior pointer method. Okay, so that is just we introduce the dual variables. Okay, we introduce dual variable y, and we use Newton method. So it's really large. It generates large systems because if A is n by n, then this is 2n. Okay, yeah, this is n. This is 2n. This is 2n. This is n. So it's a 5n. So this matrix becomes 5n times 5n. So that's a popular in the optimization world, but for this large system, it's not good at all. It's not optimized at all. Okay. The next thing is interior reflective Newton method. Okay. So this is we just minimize this problem. Okay. Okay, so this is just the ax minus b, okay, normal square, right? We just drop the constant terms. So we start at some initial point, and we follow the search directions. And if the search directions touches the boundary, then we take the path which is the deflection of this path, and follow this again, right? And it touches that, then we deflect. So we follow this way and try to find minimum. Okay. So if it touches here, and if you follow that function increases, then this is minimum. Okay. So then we find some minus gradient directions again, right? So we follow this, and this is called the interior reflective Newton method. And yeah, it seems very easy, but okay, let me show you how large iteration it takes later. Okay. Another one in optimization world is logarithm valuing method. It's a really mathematical problem. Okay, we're going to minimize this f of x, and we have a constraint. So we put that constraint as the terms in the minimization functions. So here we have log xi, log 250 minus xi. Okay, so this should be positive, this should be positive, right? So this shows that okay, we have to have the solution xi is between 0 and 205. Okay, so we minimize this problem, and mu goes to 0. Okay, so this is our two-dimensional examples. And for mu equal to 1, this function will become the likelihood. So this is level sets. So this is minimum, and as mu approaches 0, this minimum moves to here. So on this boundary, this function will become steep and steep. So if mu is very small, then the minimum approaches these boundaries. Okay, so when the minimum occurs at the boundaries. Mathematically this is good, but the solution is very approximate. Okay.
What happens when x up at 0 and 255 as your logs?
Yeah, so
it's punishing you very badly
right,
for reading the constraint.
Right.
And the earlier one you assumed it was 0 and 255.
Right. So he pushes.
Yeah, it's giving you a brutal punishment.
Yeah. Okay. Now this is another problem, another strategy from the image processing world. Okay. So this is very interesting. Actually, okay. Suppose that this is imposed problem AX2. Okay. This is imposed problem. Then we want to minimize these using this regularization. Okay. So if P is 2, okay, we call that is typical regularization. Okay, so we usually take P. Okay, so this is there is some algorithm to solve this problem. That is called ISTA. ISTA is iterative shrinking thresholding algorithm. Okay, so this is very simple. Okay, so from the xk, take the gradient of these functions. Okay, so this is minus 2a transpose axk minus b is this residual. Okay, so this is the gradient minus gradient directions of these functions, and you have the step size t. Okay, so just take some steps toward the minus gradient vectors. Okay, and we truncate. Okay, if xi is less than that, we add. Greater than that, we subtract. So this is truncation. Okay, this is the shrinkage operator. This is very simple. Okay, so the vectors get out of that range, just truncate. Okay, this is very simple idea. And in the processing world, okay, actually this is developed. This is published 4 years ago. Okay, so if t is chosen in this interval, okay, this converges to the solution of that problem. Okay, that is published in the image processing world. So
that's in the L2 converges.
actually, okay, yeah, here, yeah, this, if P is 1, okay, if P is 1, this works.
In L1.
Not L1, it's for L2.
L2.
Okay, L2. Okay. So because this function comes from the L2 functions. Okay. If this is L1, then we take different direction. Okay, different such direction. Okay. So I look at that very carefully, and I thought that okay, we can apply that idea to our problems. So our problem is also composed of that. So we have minimization problems, and we have that for terms. We have this term which shows that the constraint. If you take the x1 norm 255 minus x1 norm, then if x is between 0 and 255, this is always the same. And if x is less than 0 or greater than 255, this function will become increasing. So, okay, so I can formulate our problem into that penalty models. Okay, so we can use ISTA, and we need to design new Schritt operator. Okay, so we already know the Schritt operator for separate terms. So we combine that, we obtain this Schritt operator. And ISTA, as lambda goes to infinity, okay, we can define this Schritt operator, and we can do the same process. Very simple, and this calculation is very, very simple. Okay. Well, where is it? It's not optimized. Oh, okay. Yeah. And we have another faster algorithm, which is called FISTA. FISTA is a faster iterative shrinkage resolving algorithm. It's a kind of the SOI method for the Gaussian diagram. Okay. Because we have the arbitrary x0, and we find ISTA iterations, and we get some numbers, and we take a combination of xk and xk plus 1. Okay, so it's kind of the SOI method for ISTA. So this is called FISTA, and ISTA, the convergence case is all 1 over k, conservative is, and FISTA is 1 over k squared. So it's very fast. Okay, and so we got that Deblurring operator from the AG-Vista TV laboratory. So that comes from the experiment. Okay, so we use that, and the test image is 640 multiplied by 480. Okay, so this is original. Okay, this is wish image, and if you just turn on the backlight like that, then we obtain these images on the panels. And if you just scale down that, between 0 and 255, we get this image, then you cannot find any difference between them. So here's the errors, but here's something, right? Something white. Okay. So if you look at the digital monitor, you can see clearly. Okay. Yeah.
So this prediction system is helping you look good.
No.
Make your results look good.
No. Just this is very, very simple idea, right? Okay. So here, let me show you some numbers. Okay. So we have several numbers. Okay. Gradient projections, projected the preconditioned use. Okay. Prime dual interior Clapton Newton, lower barrier, ISTA. Even though this T is at this T, this ISTA is not convergent theoretically, numerically convergent and fast. And if you look at that, this is 3.9 seconds. Okay, it's really, it takes a long time. Okay, but this is we tested it using the method. So if we design see, I guess the speed effect could be 30 or 40. Okay, so in this case, yeah, probably at 0.1 second we can generate one image, okay, in my PC. And if you design the monitor, okay, there is a very special chip to calculate these, so we can get speed also. Okay, so this is errors, root mean square, limit error, and if you take the scaling, this is root mean square is this, and in our case, I guess this is the critical right. So yeah, so this is actually the lightning or backlight, okay, and this is the image, blurred images from that backlight. And if you look at that here, oh, there is nothing, right? There is nothing, but if you look at the digital monitor, then you see a little, okay, but that is okay. Yeah, so the conclusion is we have the box constraint image deblurring problems. This is the most simple popular algorithms, and the ISTA numerically converges and gives results. But next, we have to find L1 instead of L2. Okay, that's more complicated, more actually harder problems. Then it shows more clear images. Okay. So I have to say thanks to the aging. Okay, that's all.
Thank you.